In this lecture we are going to learn about what we call the autonomous differential equations. Autonomous equations, autonomous differential equations, autonomous equations. So what is autonomous equation? A differential equation of the form dx over dt equal a function of x only. That means it does not depend on the independent variable. Independent variable is t here, so it does not depend on that. So if the derivative does not depend on the independent variable, we call it as autonomous equation. Okay, so a differential equation of the form dx over dt equal fx is called autonomous if it does not depend on the independent variable. So in this case it is the time variable, so but it need not. So in general it can be whatever the independent variable you have in the equation, but in this case t is the independent variable, so t becomes the independent variable in this situation. Independent variable, okay, not in general. Okay, so so let's look at a situation. So let's look at first example. So let's say a Newton's law of cooling. Newton's cooling law. So if you look at the Newton's cooling law, so what is the differential equation for that? So we remember it was dx over dt equal, so x is the temperature, equal a constant, because it's going to go down, temperature go down, so k times x minus a. So here a is what we call the ambient temperature or the outside temperature, and x is the temperature of the whatever the item that we use. So for example, let's say we have a coffee cup, and so we're gonna measure the temperature of this one in this case. So x is the temperature of the cup, and then so a is the outside temperature, or what we call the ambient temperature, outside temperature. And then you can see that so this differential equation has an obvious solution, or what we call a trivial solution. So what is the trivial solution? You can see that when you plug in x equal a, the derivative is 0 and the equation is 0. So x equal a is a solution. And you can see that that solution does not depend on the time variable or the independent variable. So so we can notice few things. So for example, let's look at some cases. So what happened? So let's say if x minus a positive, if x minus a positive, you can see that. So the x minus a positive, and we also actually we assume that k is a positive constant, so we need to say that we assume that k is a positive constant. So that's the assumption. just to make the calculation easier. So now we can see if x minus a is positive, because k is positive also, with the negative sign, dx over dt, the rate of change going to be negative. So what does that mean? If x minus a is positive, the dx over dt is negative. That means x decreases. So in this case, x gonna decrease. And similarly, you can say if x minus a positive, if x minus a is positive, negative. If x minus negative, if x minus a negative, and because negative sign become positive, so dx over dt gonna be a positive. That means in this case x gonna increase. So that means we can see that it simply depend on the starting point, like whether x minus a is positive or whether x minus a is negative. So let's look at this in a graph. So let's look at the graph of this situation. So what's the graph looks like? So so what we're gonna do, the this x-axis. X-axis, x means the dependent variable in this case. This is x, and then this is the time variable. So and then we know that x equal a is a solution. So let's look at that solution. So this is the x equal a solution. So what happened now, and we notice that if you start with a positive value, like a value larger than a, if you start with a value larger than a, what will happen? X minus a is positive, so therefore the derivative is negative. So that means negative means gonna decay, so that means it's gonna go down. And the same thing, so if you start with a positive value, and then here the gap is much larger, so when the gap is much larger means we have a higher slope, so that means it's going to decay fast, like that. So that is the situation if you start with a value, so start with a value which is larger, that means x minus a is positive. Now let's see what happens if you start with a value smaller. So we start with a value smaller, that means x minus a is negative. So in that case we just saw that the derivative is going to be positive in this case, so that means it's going to increase. So that means it's going to go like that, increase. And same thing, so if you start with a value much lower, then the x minus a gap is larger, so that means the derivative, the value of the derivative is large, so that means it's gonna increase much faster rate, and it's gonna again go to that value. So this is the situation that happened in the Newton's cooling law, and you can see that. So what's gonna happen? So that means if you, so there's a physical meaning for this situation. So that means if you leave a coffee cup, if you leave a hot coffee cup, that means it is the temperature of the cup is higher than the room temperature or the outside temperature. So you can see that it's going to cool down to the room temperature. So it's going to cool down. So in this side, what happened? The temperature goes down, so it's going to cool down. And if you leave a cool object in a room temperature, what's going to happen? It's going to heat up. So that's the situation. So it's going to cool down in this case. In the first case, if x minus a is large, and it's going to heat up if x minus a is small. So this is a real situation, and you can see that this is how you can explain that using the differential equation. So let's make some few terminologies. So so you can see that so I'm going to say not. The first thing we notice is so we notice that x equal a is a constant solution. It's a constant solution. It's a constant solution. So there are constant solutions for these kind of equations. And these kind of solutions, these kind of constant solutions are called because that does not depend on the time. That means whatever the time, that stays the same. So these kind of solutions are what we call equilibrium solutions. Equilibrium. So this is called. So this is called a equilibrium. Or sometimes we call stable because it doesn't change. Equilibrium solutions. These are what we call equilibrium or stable solutions. And then we need to know some other things also, what we mean by a critical point. So the critical point. So this is the same idea that we discussed in calculus class, calc 1, critical point. So critical point means when the derivative is 0. So since we have dx over dt, so the derivative is 0 if fx equals 0. So that means if fx, we're gonna say fx naught. Let's put some. Fx naught. If fx naught equals 0, and x naught is called a critical point. Critical point. It's called a critical point at which the derivative is 0. At which the derivative is 0. At which the derivative is 0. So that means at critical points the derivative is going to be 0. So there are no changes. And the critical points always corresponds to the equilibrium solutions. So that's another one. Critical points corresponds to equilibrium points, equilibrium solutions. So there can be more than one equilibrium solution depending on the starting point. So that's why we say equilibrium solutions, because it's not one. So it can be more depending on the starting point. Good. And then you can see that in this situation, when t goes to infinity, when t gets larger and larger, you can see that the solution go to a, and then in this case we say the critical point A is stable. The critical point A is stable. So that means if when t goes to infinity, the solutions converge to that constant solution A, and we say that the solution A is a stable solution. We say that A is a stable solution. and then if a critical point is not stable, if a critical point is not stable, if a critical point is not stable, we say it is unstable. It is unstable. And the unstable case we can divide into two cases later. So sometimes we even call it half stable. So we can discuss that later. Okay, so let's look at another example. So we can look at the logistic equation. So example, consider the logistic equation. Consider the logistic equation. So what's the logistic equation is? So it is given by dx over dt equal a constant. We assume that k is positive, and there's x, and then m minus x. M is the maximum value. So here we assume that k is positive. So what this model, actually this kind of equation is going to model the population. So this model models the population. So these are for population models. Okay, model the population. And also this m is what we call the limiting value. So m is the limiting value. So what's the largest possible value it can be? So for example, let's say we look at a bacteria culture. So that's a nice population, and you can see that depending on the ingredients that they have, because it needs some kind of energy, and so there should be a maximum number it can reach, or depending on the food that they have. So that value is what we call the limiting value. So there is a limiting value for each population, because we don't have unlimited resources. There's a limited number of resources, so there is a limiting value because of that. So what are the critical points? So let's look at the critical points for this one. So critical points. So how to get the critical points? To get the critical points, what we can do, we're gonna take the fx part equal to 0. So that means in this case we're gonna set k x m minus x equal to 0. So we set it, and this gonna give you that either x equals 0 or x equal m. So there are two critical points. One critical point is x equals 0, the other critical point is x equal m. So now what we're gonna do, we're gonna consider several cases. So what's gonna happen in this case, depending on the situation. So what we can do, we can draw what we call a phase diagram. So let's talk about the phase diagram. So what we mean by a phase diagram? So we're gonna draw something called a phase diagram. So phase diagram. Or some people call it phase portrait. So what is a phase diagram? And then why we use the phase diagram first? So we use a phase diagram to check whether a solution is stable. To check whether a solution is stable. A solution is stable or unstable. So what we can do, we can check the condition. So in the phase diagram we only draw a vertical line just to meet the dependent variable, not the independent variable, and then we're going to mark the two critical points. It can be two or more. So we're going to mark the critical points here. So there are two critical points in this case. So there was a critical point 0, and there was also a critical point uh, M. So there was a critical point M and 0. So those are the two critical points that we have. Now what we're going to do, we're going to check the sign. So let's consider several cases. So we're going to consider what happens if x is greater than m, and we're going to consider what happens if x is in between 0 and m, and we also going to consider what happens if x is less than 0. So the 0, m are the critical points. So what we did, we marked the critical point and then we consider several different cases. So in the first case, if x is greater than m, what will happen due to the differential equation? So let's go back and see what the differential equation looks like. So you can see the differential equation looks like this. So it is so we write this one as dx over dt equal km m minus x m minus x. So that's the format, is m minus x. So that means in this case, so if you pick a value which is more than m, if you value more than m, what will happen, one factor become positive, one factor become negative. That means the product is negative. So in that case, what will happen, so we can write this one first. So since this is the first one, dx over dt, so which was k x m minus x, and you can see that if you pick a value which is greater than m, this factor going to be negative, this is going to be positive, and we assume that k is positive, so that means this product going to be negative. So the product negative means the slope is negative, so that means x gonna decrease. So since x decreases, what we gonna do, we simply draw an arrow indicating that x gonna decrease. So that's what we do, we just draw an arrow indicating that x gonna decrease if x is greater than m. So if we start with a larger value which is more than m, it's gonna decrease. Now do the same thing. So if you go to the other case, so you can see that dx over dt, which is kx m minus x. So in this case again, so what's going to happen now, if you pick a value in between the two, and you can see that this is automatically positive and this is also positive, because you pick a value which is smaller than m, larger than 0. So that means the product is positive. So that means in this case what's going to happen, x gonna increase. So that means what we're going to do, we're going to draw an arrow saying that it's going to increase. So that means in the whole interval is going to increase. So we can sometimes put two arrows just closer to each critical point. You really don't need that, but it can help you. And then the last case. So what's the last case? So you can see that x is negative, smaller than the lower critical point. So in this case, dx over dt, which is kx m minus x. Now what's going to happen in this case? So you can see that x is negative, so this is going to go down, and then so what will happen to the m minus x factor? So x is a negative value, but with the negative sign is going to be positive, so this is going to be positive. So that means the product going to be negative, so that means it's going to decrease. So in this case, it's again going to decrease. So that means we're going to draw an arrow indicating that it's going to decrease. So what does that mean? So you can see that if you start with a value closer to m, it's going to reach to m. See that if you start with a value either larger m or small m, what will happen? It's going to reach to m. So that means we call this m is a stable point. So this is stable. This critical point is a stable critical point, because both sides can converge to m. But if you look at 0, what will happen if you stay near 0? If you start with a value near 0, you can see that both values going to go away from it. Both values going to go away from it. So that means we call this is a unstable critical point. So this is unstable. So the stable means both sides has to converge to that point. Unstable means if at least one go away, we call it is unstable. But in this case, you can see that it's going to go away from the critical point, so we call it is unstable. So these are the cases that we have. So we have if the two sides going to converge, both sides, we call it is stable. So we call this is stable. If the both sides going to go away from it, we call it is unstable. And then what's going to happen? So there are two other cases. So there's a one case, this is going to go in, this is going to go out. Or the other way, you can see that this is going to go out, this is going to go in. So in this case, we call this a half stable. Half stable. So this is a part of unstable situation, but we call it half stable because in one side is going to converge, but the other side is going to go out. Okay, so so let's look at one more example. So the next example, consider dx over dt equal 0.1 x 5 minus x, where k is 0.1 and we assume that this is positive, so that's good. So this is a part of a logistic equation. This is one of the special case of a logistic equation. So what are the critical points? So you can see that the critical points are, so what we can do, we're going to say this equal to 0. So we're going to say 0.1 x 5 minus x equal to 0. So this says that x equal 0 or x equal 5. So those are the two critical points. Actually, and it would be much better in this situation. Okay, so there are two critical points, 0 and 5. So now what we're going to do, let's look at the slope field, because we know that what is the slope field looks like, because this is a differential equation. So then we can draw the slope field. So the slope field is also going to give you like a really nice idea about this. So let's see what's gonna how the slope field looks like. So for this differential equation, the slope field looks like this. And then so this is the time variable, so this is a t, and this is the x, this x variable, and so we have one critical point here. So this is the x equals 0 critical point, and this is the x equal 5 critical point. So we have two critical points, and then you can see that if you start below the lower critical point, and you can see that it's going to be negative, so that means they are going to go out of it. So in this case it will go out. You can see it's going to go out. If you start below, it's going to go out. And if you start between 0 and 5, what's going to happen, as we discussed, it's going to increase. It's going to increase. So here what will happen, x going to decrease. In this part, x going to increase, and here x going to decrease. So it's going to increase, and then if you start with a value above 5, so if you start with a value between 0 and 5, you can see they are increasing. If you start with a value above 5, what will happen, the slope is negative, so that means it's going to decrease. So you can see that if you start with a value closer to 5, both sides going to converge. So that means this is a stable point, as we discussed. This is stable because both sides going to converge to number 5. So that means in the long run, you end up with a value 5. If you start with any value between 0 and if you start with any value above 0, because if you start with 5, you can see that the slope is 0. That means you're going to start with a constant value, so it's going to be constant if it is 5. But if you start with any value more than 0, and you can see that the both sides going to converge to 5. Both sides going to converge to 5. Now if you start with 0, it's 0 because the slope is 0. But if you start with a value below 0, so what will happen below 0, you can see that it's gonna decay because it's gonna go down. So good. So good example would be like, you put some money in a bank, a situation like that, because for populations you cannot start with negative values. So good. So in a bank, what will happen, you have a debt. So what so if you do not pick this constant correctly, so what's going to happen, you're going to be you have more debt in the long run, so it's not going to be good. Okay, so so that is the situation. And then you can see, so we can draw as we did before, we can draw the phase diagram for this one. So and then you can see in the phase diagram it's very clear. So if you start with more than 5, it's going to go down. If you start with between 0 and 5, it's going to go up. If you start with below 0, it's going to go down. So we can draw the phase diagram for this situation. So in the phase diagram, so you mark a vertical line, and then you draw the critical points, 2 critical points. One is 0, the other one was 5, and then you can see that if you start with the larger value, it's going to go down. If you start with the value between, it's going to go up, and if you start with the value lower than 0, it's going to go down. So that means, as we discussed before, x equal 5 is stable, and then you can see x equals 0 is unstable. So that's unstable. So we can also say that so xt, so the limit, so we can say the limit of this function, so we can say the limit when t goes to infinity, xt equal 2 cases. So what's going to happen, so what's going to happen in the long run, so you can see that in the long run, so if you start with the value more than 0, if you start with the value more than 0, it's going to go to 5. So it's going to go to 5 if your starting value, that means x0 is more than 0. So if you start with a value which is larger than 0, you can see it's going to converge to 5, and it's going to stay 0. It's going to stay 0 if the starting value is exactly 0. If the starting value is exactly 0, it's never going to increase. It's going to stay there. It's like you have to start with a population with 0. There are no production. You can stay there. And then you can see that it's going to go to negative infinity. Negative infinity if you start with a negative value. So if you start with a negative value, it's going to go to a negative infinity. So we can write something like that in this situation. It's just directly coming from the phase diagram. Let's do one more example just to learn the idea. So we can say analyze. You can say analyze. What happens what happens when t goes to infinity of dx over dt equal negative 0.1 x squared x minus 1 x minus 1. So as before, what we can do, we can find the critical points. So we're going to find the critical points. So that means you're going to set negative 1 x squared x minus 1 equal to 0. it says that x equals 0 or x equal 1. Now as before, we can draw a vertical line, mark the critical points. So we have 1 and 0. Now what we can do, we can consider cases. So we can consider what happen if x greater than 1, what happen in between, what happen x less than 0. So let's pick a test point. So what we normally do, we pick a test point and check the sign. So it's negative 0.1 x squared x minus 1. So if you pick a value which is larger than 1, so what are the signs? If you pick a value larger than 1, so this is going to be plus, this automatically plus. So it is plus plus with a minus sign, so it's going to be negative. So that means dx over dt is negative, so x gonna go down. So that means this one we have a down arrow. So let's do the same thing. So we have negative 0.1 x squared x minus 1. As before, if you start with a value between 0 and 1, this is negative, or we can put negative sign. So so this is going to be negative because you start with a value between 0 and 1. This is negative, this is positive. So you have two negative signs, that means this is positive. So that means dx over dt going to be positive, so that means x increases. The last case, in that is again negative 0.1 x squared x minus 1. So let's check the sign. So if we start with a negative value, this is still positive. It's a negative value, so negative minus negative is still negative, so this is negative. So negative negative is going to be positive. So that means dx over dt is positive, that means x increases. So in this case, so here it increases, this is also increasing. So now you can see what's going to happen depending on the arrows. So the x equal 1 is a stable point, so this is going to be stable, this is going to be stable, and you can see here arrows, one going in, one going out, so you can see half stable. So half stable, half stable. And then you can look at the long time behavior for this one. So you can see if you start with a negative value, or 0, it's gonna reach. If you start with a negative value or 0, it's gonna go to 0. And then you can see that it can never pass that value, because after you go to 0, because that's a stable, that's a critical point, it can never pass the critical point. You're going to stuck with the critical point, you can never pass the critical point. So that means if you start with a negative value or 0, it's going to stuck with 0. And then if you start with a positive value, whatever the value, it's going to reach 1. So so this is like interesting situation. So that means if you start with a negative value, it's going to go to 0 and stop there. And if you start with a positive value, it's always going to reach that number 1 value. So that means we can write this. So we can say the limit when t goes to infinity, xt, I have two values. So one value is going to go to 1 if the starting value, that means x0, is positive, the starting value, and it is 0 if the starting value is either 0 or negative. So that is the long term behavior, the long term behavior. The long term behavior. Okay, so now as the final example, let's look at the general logistic equation, the general logistic model. So general logistic model, general logistic model, general logistic model. So what's the general logistic model? So this is we write this one as dx over dt equal kx m minus x, and what we're gonna do, what we call harvesting term. That means you're gonna take some thing out, like you have seen, like, you know, there are some coin machines. You're gonna put some coin, but in time to time someone come and take the coin out, because otherwise it's gonna fill out. So that's what we call harvesting. So we're gonna add a term like that. So you're gonna take out from the population, you're gonna take something out in time to time. It's called harvesting term. Harvesting. It's also gonna decay the rate. So so we call h, that's the harvesting rate. Harvesting rate or the decay rate, decay rate, because that term gonna decrease the rate of the x. And then again, m is the population size at time t, x is the population size, m is the maximum value, m is the maximum value, and x is the population size. So x is the population size, at time t. So what's the population size at time t? So this is what we call a general logistic model. So let's try to solve this. So how to solve this kind of equation? So we just follow the same routine work. So we're going to start with four critical points. What we're going to do, we're going to set dx over dt equal to 0. So that means in this case, what's going to happen, you're going to get kx m minus x minus h equal to 0, and then you can see that this is a quadratic equation. So this is a quadratic equation. It's a quadratic equation. So what we can do is we can write this in ax squared plus bx plus c form. So we can expand this first. So if you expand it, this is going to be negative kx squared, and then plus k mx, and then you're going to get minus h equal to 0. And if you remove the negative sign, you end up getting k x squared minus k mx plus h equals 0. Now what we can do is we can use the quadratic formula to solve this. So let's use the quadratic formula to solve this. So we have x equal negative b plus or minus b squared minus 4ac square root over 2a. So let's plug in. So if you plug in, so minus b, that means km, plus or minus km squared minus 4kh square root divided by 2a, 2k in this case, 2k. So if you simplify this a little bit, you're going to get km plus or minus, we have k squared m squared minus 4kh square root over 2k. Now what we can do is we can divide the top and bottom by k. because k is a common term, so we can divide by k. So if we divide by k, inside the square root you have to divide by k squared, because there's a square root sign, so it's going to cancel one of the powers, so that means you have to divide by k squared. So if you divide outside by k, you divide inside by k squared. So that means you're going to get m plus or minus m squared minus, if you divide by k squared, so inside you divide by k squared, so you're going to be 4h over k square root over 2. So to get, so you can write this one as m over 2 plus or minus 1/2. So you can write this one as m squared minus 4h over k square root. So that is the discriminant. So this is what we normally call discriminant term. This whole term is called the discriminant. So that means depending on whether this is positive, 0 or negative, you're going to have two real, equal real or complex roots. So let's consider the three cases. So there are three cases. So the first case is if m squared minus 4h over k is positive. So if this is positive, you're going to get two distinct real solutions, two distinct real solutions. So you're going to get two critical points. So you're going to get two critical points in this case if this term is positive. The second case, if this term is exactly 0. If this term is exactly 0, what's going to happen? We have a unique critical point. Unique critical point. Unique critical point. So that the unique critical point can be stable or unstable. So we don't know. So this can be either stable or unstable. It depends on the other terms that we have in the differential equation. So that means so the graph gonna look like so this is this one of those critical points. So it can be like one going like that, the other one going like this. So in this case, this is going to be one side is coming in, one is going out. So but it depends. So that's why it can be stable or unstable, not always stable. And the third case is, that's the last case. Third case is if m squared minus 4h over k negative. So it can be negative. If this is negative, what's going to happen? You have no real critical points. So that means since there are no critical point, there is no way it can converge. So that means this case is always unstable because there are no critical points. So we have to converge. So it's always unstable in this case. Always unstable. So that means in practice, what's going to happen? The final solution in the long run, it either going to go to negative infinity or it's going to go to positive infinity. So there are no other cases. So it has to be one of them. So in the next, so let's look at three cases for those three situations. So what we can do, we're going to pick the m. We're going to pick the k, m and h, so that we're going to have those three situations. So let's look at the first one. So this is the first situation. So in the first situation, so what will happen? So we're going to we pick the k M and H show that there are two solutions. So this is the first solution. So this is like roughly, I'm going to say the first solution A. This is roughly 6.45, and here this is roughly 1.65. And then we discussed a similar situation before, and then you can see that in this case the bottom one is unstable because it's going to go out, and the top one is stable. So one is stable and unstable. So this is the situation. So here we get this stable one, and you can see that this is unstable. Stable and unstable. The top one is stable because it's gonna, or both gonna converge to this critical point. But here you can see that this is gonna go away from it. This also gonna go away from it. So that's gonna be unstable. So in this case, so this is the first case. So we can say case 1. One is stable, one is unstable. Situation, there are two distinct real critical points. Two distinct real critical points. So let's look at the next case. This is case number 2. The case number 2, what will happen? So there's only one critical point. So you can see that the both critical points converge. It's going to be A equal B equal, you can see it is 4. So and then what will happen? In one side gonna go out, the other side gonna go in. So this is a half stable situation. So in other words, unstable, because it's not stable. Okay, so you can see the unstable, or you can say half stable. Because the top, if you start with the value more than 5 or equal to 5, it's going to converge to 5. But if you start with a value lower than 5, it's going to go away from it. So this is like kind of like, you know, if you have like a mechanical system, when the system gonna converge. So like, you know, for example, you have a voltage system, you have a circuit. In a circuit, like, you know, if you start with some kind of voltage, what's gonna happen? It's gonna reach a particular value. But if you start with a low value, or maybe charge, if you start with a lower charge, the charge gonna go to infinity, like, you know, negative charge gonna go to infinity. So that's like, you know, start with a low value because it's gonna go to negative infinity. So you can always find some physical relations between those situations. So that's a like kind of good practice, you know, how to combine these results with something that you know in other field. So let's look at the last situation. So this is the case number 3. So in this case, you can see that there are no critical points. When you try to solve it, you're gonna get complex numbers. So that means there are no real situations. So what's gonna happen in both cases? You can see go to infinity, negative infinity, go to negative infinity, and also go to negative infinity. So each solution end up in negative infinity. So it's gonna decrease. So you're gonna go to negative infinity. There are no real situations. So this is what I should say a very dangerous situation, because what will happen is gonna go to negative infinity. No matter where you start with, is end up in negative infinity. Okay. So yeah. So what I'm gonna tell you, like in a general logistic model, depending on the value we pick, it can end up with any situation. Sometimes you have two real solutions. So in that case, one can be stable, one can the other one can be unstable, or both can be unstable. So depending on the other coefficients, and also there can be a situation there's only one critical point because they're going to converge, and in that situation, what will happen? So either it can be stable, or it can be unstable, or half stable. And also there can be another situation where there are no critical points. That means the only option would be it gonna go to infinity, or like completely unstable because there are no critical points. So these kind of systems, like we don't need this to a real world situation because those solutions are not gonna converge. Okay. So that's the end of the autonomous equation discussion.